Okay, so this is our Fourier transform. Uh, this is our Fourier transform scene. Okay, so Fourier transforms are based on the idea that you take any kind of function, any kind of signal, and you can reproduce it by summing together sinusoidal function sine waves. So, for example, what I just showed you is I can reproduce a Gaussian function by adding together, looks one, two, three, four, by pretty well by adding together six cosine waves, and if I added some more, I could make the approximation even better. And so the Fourier transform makes use of the fact that you give me any function and um, and I can reproduce it. The only trick is I have to know what are these coefficients that I have to multiply each of these cosine waves by to get them to sum to reproduce the original function. And the way I get those coefficients is through this operation called the Fourier transform. So if if I have my Gaussian function and I give it to my computer and ask what is the Fourier transform, then out comes another function that I'll call g of u. So this is a function of spatial frequency, and the values of this output, these are actually the values I use to scale the cosine functions that I showed you before. So the Fourier transform just tells us the sizes of the coefficients, but because I can reproduce any kind of reasonable function by summing together cosine and sine functions, if I have the coefficients, that contains exactly the same information as the original function. So that's the cool thing about the Fourier transform. It just tells us coefficients, but it contains all the information. And it turns out that that the Fourier transform is a sort of interesting integral. You take your original function, you multiply it by, yes, a complex exponential that's the product of the original spatial variable and the frequency variable, and you integrate it all up, and you get something that has no spatial information in it at all. It's just frequency information. So here's another one. This is a more challenging function to do a Fourier transform. You take something with a sharp-edged pulse, and you start adding together cosine functions. And as we uh, as we add together the cosine functions, first it's kind of interesting that because the particular form I picked every other coefficient is zero. And the other thing is the coefficients are alternating in sign. And this thing does not converge quickly at all. The Gaussian function converged really quickly, but this one didn't. And if we go and ask a computer what the Fourier transform is, we get this horrible looking function that's sine pi u divided by pi u. U is the spatial frequency. It's also known as the sinc function, and it's horrible because it decays very slowly. It decays as 1 over u, and is infamous for having all of these ripples. So what do we learn from this? Well, there's this general principle that if you have something that is sharp in your starting function, the Fourier transform is going to give you lots of ripples. But still, this still works. You know, you ask the computer to give you the coefficients, and you can then reproduce the original function. And in this case, you want to use more coefficients to try to get a better approximation. Um, so what we have just seen is that if I give you this Gaussian function, the Fourier transform happens to be a Gaussian function. If I give this rectangular pulse, I get this sinc function. Um, this is another interesting one, a delta function, which is just a spike, turns into a constant in the frequency domain. And Fourier transforms have all kinds of interesting properties that I'm not going to tell you because we only care about a couple properties. One of the most important is convolution. Now, convolution is a filtering operation. Uh, what we do is we say, let's suppose that we have a signal that I'll call a G, and we have a kernel called H. And what we're going to do is to get every output point, we're going to look in the vicinity of output point at value X. We're going to look at the vicinity of G, perturbed by S, and we're going to multiply it by the magnitude of the kernel at that value of S, and we're going to add it all up. So what that means is, here's the output of the convolution. And so, for example, if I want to compute the value of the output at this value, I'm going to look at the neighborhood of that value in the input signal, and I'm going to weight it by the magnitude of this kernel. So the net result is that I'm doing a smoothing operation because I'm taking multiple points of the input, weighting it by this kernel, and out comes something that's smoother. You see that? So this is what convolution is, and it's exactly what happens when a microscope looks at an object. You might say, well, the object has lots of ripples in it, but the microscope has a point spread function that is broad, and so what you really get is some kind of smooth version. Or in an old-fashioned hi-fi system, you have a treble control, and if you turn the treble control down, you're in effect convolving the signal that represents the sounds with a kernel that's broad. Okay, so it turns out that Fourier transforms are really cool because because of this property, that convolution of two functions is represented in the Fourier domain as just the product of the two Fourier transforms. And that turns out to be really useful. It's vastly faster to do the Fourier transform, multiply the two functions together, and transform back to do this convolution operation. That's because the Fourier transform on the computer is really, really fast, thanks to a really nice algorithm. Now, the other thing is, if in the Fourier domain, it's just the product of the Fourier transforms of the two functions, shouldn't we be able to take this filtered, this smooth signal and work back to that one? All we would have to do is divide by h of u. So we take the result, we divide it by h of u, and get some kind of g back. So that's a deconvolution operation, and doesn't always work well. So here's our filtered signal. In orange here, I show the unfiltered signal, and so we try to do 1 over h of u, and h is big H of u is a very narrow thing. You do the deconvolution, and it works kind of well, but this sharp pulse blows up. So anyway, deconvolution doesn't always work, but it's a really cool idea that you could make use of this property of Fourier transforms to try to do it. And we'll be talking about that in removing the CTF in a few minutes. Okay, so in 2 dimensions, which is where we use Fourier transforms in image processing, it's the same kind of idea. So we build up. We have a function, and we can build up a duplicate of it by using coefficients, which I'm displaying here as grayscale, and gratings. So what I'm showing here is coefficients of gratings of various periodicities, various spatial frequencies. And in this case, I have to fill in gratings going vertically, horizontally, and diagonally, and that's why I have this two-dimensional array of coefficients. But once I uh, added together some number here, what is it, about 12, uh, 12 different gratings, I can reproduce the original function quite well. Okay, so it's the same idea. We are reproducing the original function by adding together sinusoidal components. And in case you like this stuff, it's exactly the same formula, except that now we have x and y in it, and we have u and v in it. So u and v are the two frequency variables, x and y are the two spatial variables. And it has the same kind of properties, but there again, I'm sparing you most of the Fourier transform lecture because there are only a few properties that we really care about. One is convolution, again, another is rotation, and another is projection. So let me talk about these three properties of the 2D Fourier transform. So convolution in 2D is, again, just like convolution in 1D. I have a kernel, and I have the original signal, and out comes the convolution. And so here's an example. You have a light microscope, and you have an object like that. Your light microscope might have a point spread function that looks like that. And then here's the image that you get. In the image you get at any point of the image is going to be the neighborhood of the points on the actual object weighted by this kernel. And you can see how the Fourier transform approach works. So this is the Fourier transform of my smiley face image. It's in color because the different colors represent different phases. We'll talk about that in a little bit. This is the Fourier transform of this Gaussian kernel, and this is the product of the two. So when I make the product, what happens is that the farther out points, that is the higher spatial frequency points, are set to zero because they're zero in the kernel. When I transform back, then I get my convolved object. So it's almost easier to imagine what's happening in the Fourier transform of the image than in the actual part of the image, and it goes vastly more quickly on a computer, which is why when people write reconstruction programs and so on, they're often switching between Fourier space and real space, whichever is quicker. Now, here goes the effect of the contrast transfer function. Let's suppose that we had a random object and we want to operate on it with the contrast transfer function of an electron microscope in phase and defocus contrast. Well, here's a representation of the CTF in 2 dimensions. The colors are such that red is positive and blue is negative, and so this is our familiar oscillating negative, positive contrast transfer function. This turns into a point spread function that's sort of complicated, and nobody thinks about that because it's so much simpler to do the Fourier trick. So what we do is we have a random object. We take its Fourier transform, which also looks like a random object. We have the contrast transfer function. We take the product of the two, and this is what we get. We get the beautiful colored random phases, and there are zeros here, which are the zeros of the CTF. Now, if I transform back, this is what my image would look like under phase contrast imaging, and you can see it's kind of gotten this rough, ripply kind of look, which is what it looks like if you look at a carbon film in the electron microscope. Now, there's one other thing you can do, which is instead of actually looking at the Fourier transform, this y tilde, we compute the magnitude squared of the y tilde, and so that gets rid of all the colors. This is the image that you see on um, the computer for your electron microscope that shows these dark tone rings, and gives you an idea of what the CTF looks like. So this is the power spectrum that I was talking about before. So the contrast transfer function of an electron microscope is most easily described in the frequency domain, and so what everyone does is follows this path to simulate an image in the electron microscope. There are other cute things you can do with convolution. For example, crystallography is best understood, I think, as a convolution. You have an object, you have a kernel, which is a lattice. If you convolve them, you get your object repeated in a lattice, but the the Fourier transform of that is just the product of this and that. So if you take the continuous transform and you sample it at discrete points, and you do the inverse Fourier transform, you get a lattice of your original object. And if you pick the wrong lattice, you get overlap. You get what's called aliasing from not sampling the original transform finely enough. Okay, so there are two other properties that are really cool and that we use in 3D reconstruction. One is the rotation property, and that just makes use of the fact that in the exponent we have what looks like the dot product between x, the spatial variables, and u, the frequency variables, and so a dot product is invariant under rotations, and that in fact is what happens. So if you rotate the smiley face, you rotate its Fourier transform. So rotation of real space turns to rotation in Fourier space. And then finally, there's the projection theorem. So we're taking a CAT scan of your body, right? And so the way the CAT scan machine does is it sprays. This is a slice of your body, and the CAT scan machine sprays X-rays along in one direction, uh, and uh, and and a detector gives you a one-dimensional projection of of your density. Now the trick is that um, if you take you can also think about this 2D density of a slice of your body as some Fourier transform function. Now the cute thing is that the Fourier transform of this 1D projection turns out to have exactly the same values as the value of this Fourier transform along a single line, along a single slice. The way this works is a projection is an integral. So, for example, a projection along y is just an integral over the y variable. And the Fourier transform is an integral too, and it turns out that we can just convert part of this integral into a projection by just saying, okay, let's look at the 2D Fourier transform with the v, the second frequency variable being 0. So this is exactly, if you work this out, the 1D Fourier transform of the projection of that of that function. Now, the rotation property says that we can rotate u as we're taking these 1D projections, and as we rotate u, we're in effect rotating this thing, and that is the same as inserting slices at various angles. And if we insert enough of these slices, then we can actually reconstruct that, and we can do an inverse transform, and we can get the result of your CAT scan. So that is that's how you can do a 2D reconstruction. We'll talk more about this in a little bit. Now, the discrete Fourier transform is what's calculated on a computer. So this is the beautiful continuous mathematical object. And this is what happens on a computer, which is that we just replace the integrals with sums, and otherwise it looks pretty much the same. And so this is what the discrete Fourier transform looks like. It takes an image, let's say, of 32 by 32 pixels, and it converts it into another representation, which is also 32 by 32 pixels, but the quantity at every pixel has an amplitude and a phase. It's a complex number. And immediately you should say, well, gee, a complex number has two parts. It has a real and an imaginary part, and so there must be twice as much information here as there. There's something wrong. Well, it turns out that the real part and the imaginary part are each centrosymmetric. The real part is even, and the imaginary part is odd, and so there is a more efficient representation that where you could say, well, this thing is actually the same as 32 by 32 array of real values, but mathematically it's easier to let them be complex. So there isn't any trick, there isn't any gain of information.
Fred, you're breaking up. I don't know if that's internet on our side or your side.
Hello, test, is that? Am I?
Okay, we can hear you. Am I coming in clear or am I choppy as well?
No, you're coming in perfectly clear. Okay. Well, I haven't gotten any warnings from Zoom yet. Tell me if it's continuing. I can switch to a different internet, a different Wi-Fi.
Okay. We'll plow ahead.
We'll plow ahead. Okay, so now the scaling of the discrete Fourier transform is important to note. The issue is what is the size of a pixel in the Fourier representation of an image, and this is something that's going to come up in real life. Let's say this is a micrograph, and this is its Fourier transform, and you want to know, okay, so what's the maximum resolution that I can get out of this micrograph? And the easy way to do that is to say, well, what is the maximum spatial frequency that's represented by the Fourier transform? So here's how it works. We say dx and du are the pixel sizes of the two representations.
You're breaking up. I'm wondering, what is your microphone? Are you using AirPods?
I'm using AirPods, and I'm going to switch to the other AirPod.
We're also checking on our side because
yeah. Okay, let's see if it was a dead iPod, AirPod. So the question is, what is the size of a pixel here, and what does that tell us about the resolution? So the size of a pixel du is equal to 1 over n dx. That is, the size of a pixel here corresponds to the entire width of the original object. That is, the very first, as you move from one pixel to another, you're increasing the frequency of the grading by one cycle per the entire width of the object. Now, what about this? What about well, this is zero frequency in the center, and this is high frequency over here on the edge. N of the frequency pixels, n over 2 of the frequency pixels. So what is that? Well, this frequency here, well, the entire width, n du, corresponds to 1 over dx. So half of this corresponds to 2 pixels there. The conclusion is that if we say that 1 over dx is, we'll call it the sampling frequency, that sampling frequency is twice the maximum accessible frequency, which is n du over 2. So let's do for example, let's suppose that this is our micrograph, and at the magnification we're using and so on, 1 pixel is 1 angstrom. The edge of the Fourier transform here is a spatial frequency of 0.5 per angstrom. That is, it represents a resolution of 2 angstroms. And this is a representation of the all-important sampling theorem that says that the highest frequency that you can recover from a sampled image is half of the sampling frequency. This is the Nyquist theorem, and people will say, well, the Nyquist frequency is the edge here, and the Nyquist frequency is always half of the sampling frequency. So anyway, so that's what this scaling is, and that's useful because you're looking at DFTs all the time when you're looking at Fourier transforms of images.